Calculus often looks like an impenetrable wall of strange symbols, but underneath all the Greek letters and complex notation, it is simply a tool designed to do one thing: measure how fast things change in real time. In the next 5 minutes, you are going to learn a reliable 4-step recipe to calculate your very first derivative from scratch. We are going to prove exactly what happens to the slope of the equation y equals x squared. To do this, you only need 3 things: a piece of paper, a sharpened pencil, and some basic algebra. Specifically, as long as you remember how to expand x plus h squared, you have everything you need. Calculus applies standard algebra to moving targets. Think of a mathematical function, like y equals f of x, as a literal machine. You put an input, x, into the machine, and then it hands you back a modified output, y. When those inputs and outputs shift, mathematicians use the Greek letter delta to track it. Delta simply means change. To find it, you just take your new value and subtract your old value. This animated thermometer shows exactly how that calculation works. If the morning temperature is 65 degrees and at night it drops to 57, you calculate the change by taking that final temperature of 57 minus the starting 65. The result is a delta of -8. So whenever you see delta x, just read it as the change in x, and delta y is simply the change in y. Notice how the temperature went down, but we still measured a change. In math, an increment doesn't always mean growth. It is strictly a measurement of the difference between a starting state and an ending state. If we want to compare how these two variables move together, we divide them. Dividing the change in y by the change in x gives us an average rate of change over a specific distance, very similar to calculating average speed over a road trip. Look at this graph showing an ant on a steep, curved hill. If the ant wants to know how steep its climb is, we can measure the horizontal change and the vertical change between the ant and a second point further up the curve. But dividing those distances only gives us the average slope between those two spots. The hill curves, so the steepness is always changing. To find the exact rate of change exactly where the ant is standing right now, we have to slide that second point closer and closer. The gap between them must become incredibly tiny. We call that tiny horizontal change h. To get a perfect measurement, we use a mathematical tool called a limit to push that gap, h, as close to 0 as physically possible. That is what a derivative is. Written as dy over dx, it is simply the exact local slope you find the moment that horizontal gap vanishes. We can find that exact slope for almost any equation using a universal 4-step framework.
Step 1. Take your initial input, x, and give it a tiny nudge forward by replacing it with x plus h. Step 2. Find the change in your output, delta y, by subtracting your old y value from your newly calculated y value. Step 3. Take that resulting change in y and divide it by your tiny initial horizontal change, which we called h. Step 4. Apply the limit. Calculate what happens to your equation as that gap, h, shrinks down to 0. If you follow this recipe in order, it turns the abstract idea of a derivative into a predictable mechanical routine. Grab your piece of paper and write down our target equation, y equals x squared. Let's run it through the machine. Step 1. We give that blue x a tiny increment. Replace it with x plus h. For step 2, we need to find our new y. Because our original function squares the input, we have to expand the binomial, x plus h squared. That multiplies out to x squared plus 2xh plus h squared. Now, to finish finding the actual change, delta y, we must subtract the old y value from this new string of terms. Our old y was simply x squared. Look closely at the equation. The original x squared and the minus x squared perfectly cancel each other out. This isolates our change in y, leaving us with exactly 2xh plus h squared. On to step 3. We take this isolated expression for our change in y and divide the entire thing by our tiny change in x, which is h. Here is where many beginners make a mistake by trying to divide just one part. Before you cancel anything, you have to factor the numerator. Pull an h out of both top terms so it sits on the outside of the parentheses. Now, the red h multiplying on top and the red h dividing on the bottom perfectly cancel each other out. The fraction disappears, leaving us a clean 2x plus h. Finally, step 4. We take the limit.
We shrink that horizontal gap down until it is 0. As h becomes 0, our equation of 2x plus 0 solidifies. The gap is gone, leaving our final answer. The derivative is 2x. By carefully expanding the terms and factoring them out, we entirely bypassed the paradox of dividing by 0, allowing us to find the precise, instant rate of change. You just performed differentiation from first principles. You proved, step by step, that the rate of change for x squared is exactly 2x. This graph of x squared shows why that formula is so powerful. It allows you to pinpoint the slope at any location on the curve instantly. At x equals 1, the slope is 2. At x equals 5, it steepens to 10. You took the basic idea of an average rate of change, applied a limit to shrink the measurement gap, and produced a precise derivative. Now it's your turn. Take your piece of paper, write down y equals x cubed, and run it through those exact same 4 steps.